We can now look at homogeneous equilibrium or homogeneous equilibria. In this case, it means reactants, and products exist in a single phase. Okay, reactants and products exist in a single phase. For the gas phase reaction, this one, any two or four, then it forms the 2NO2. Okay, so you can see both the reactants and the product are in gaseous state. So this is homogeneous. So we can write the case expression for this one, which is NO2 squared over N2O4 over N2O4. Okay, so now we can also express gas phase expressions. Gas phase expression can be expressed. Gas phase expressions can also be expressed by Kp. Gas phase expression can also be expressed by Kp. Okay, so we were using K here, we use Kc, so we can also express it by Kp. Okay, so the Kp expression is written using equilibrium partial pressures. So Kp expression is written using equilibrium partial pressures. Partial pressures of reactants, equilibrium partial pressures of reactants and products. Equilibrium partial pressures of reactants and products, just as Kc, which is written using equilibrium concentrations of reactants and products. Okay, so now for this reaction we can also express it using Kp. So this reaction will be now Kp is equal to the partial pressure of NO2 squared over partial pressure of N2O4. Okay, so that is how we can express this reaction using Kp. Okay, but now how is this Kp related to Kc? What is now the relationship between Kp and Kc? Okay, so relationship between Kp and Kc. Relationship between Kc and Kp. Okay, so since pressure and molarity are related by the ideal gas law, we are now going to pressure and molarity are related are related by the ideal gas law. We know that the ideal gas law is PV equal to nRT. Okay, so won't go into details to show you how this is derived. So now we can straight away go into the equation. Okay, so now Kp is equal to Kc. Kp is equal to Kc RT delta N. Okay, so this is the relationship between Kp and Kc, where R is equal to 0.08206. So R is the ideal gas law. R is 0.08206 liter atmosphere per Kelvin per mole. Okay, then T is temperature in Kelvin, or Kelvin temperature. Then delta N. We can see we have delta N. Delta N is moles of gaseous products. Moles of gaseous products minus moles of gaseous reactants. Reactants. Okay, so then we know Kp and we know Kc. All right, so now we can have a situation whereby Kc is equal to Kp. So when does this occur? Okay, so Kc will equal to Kp when the number of moles of the reactants, and the products, or the number of gas molecules, when the number of gas molecules is the same on both sides. Okay, so if the number of gas molecules is the same for both the products and the reactants, it means delta N is equal to 0. So if delta N here is equal to 0, 0 to the power RT is equal to 1. So now Kc becomes equal to Kp. Okay, so it is now your job to find out whether a given reaction, for a given reaction, the Kc or Kp are equal or not equal. Okay, so let's have an example. So does Kc equal to Kp? Does Kp equal to Kc for A? So let's look at this reaction. Hydrogen gas plus fluorine then forms hydrogen fluoride gas. Okay, so does Kc equal to Kp for this reaction? So what we just need to find is delta N. So in this case, delta N is equal to 2 minus 2. Here there is a 1 plus 1, which is equal to 2. So it's equal to 0. So in this case, our delta N is equal to 0. So Kc is equal to Kp. Okay. Then another reaction. sulfur dioxide gas, sulfur dioxide gas plus oxygen gas, then forms the sulfur trioxide, 2 sulfur trioxide. Okay, so does Kc equal to Kp for this reaction? So delta N in this case will equal to 2 minus 1 there, 2, so 3, which is equal to negative 1. So in this case, delta N is equal to negative 1. So Kc is not equal to Kp. Kc is not equal to Kp. Okay. So moles of the reactants not equal to the moles of the products. So if the moles of the products and moles of the reactants are the same, then Kc is equal to Kp. Okay. So let's have another example. For the reaction, for the reaction of nitrosyl, for the formation of nitrosyl chloride, for the formation of nitrosyl chloride. So this is the equation: 2NO plus chlorine then forms nitrosyl chloride, NOCl gas. So this is nitrosyl chloride. Okay, so this reaction was studied at 25 degrees Celsius, or studied at 25 degrees Celsius. So the equilibrium partial pressures, were found to be equilibrium partial pressure of nitrosyl chloride is equal to 1.2 atmospheres. Partial pressure of nitric oxide is equal to 5.0 times 10 to the power 2 atmospheres. Okay, then partial pressure of chlorine gas is equal to 3.0 times 10 to the power negative 1. Okay, so the question is calculate the value of Kp. Calculate the value of Kp. Calculate the value of Kp. Okay, so this is straightforward. So what we need to do is just write the Kp expression from the equation given for the formation of nitrosyl chloride. Okay, so solution. So we simply write Kp. So Kp in this case will equal to partial pressure of nitrosyl chloride squared over partial pressure of NO times partial pressure of chlorine. So NO squared times the partial pressure of chlorine. Okay, then now we substitute the partial pressures. So partial pressure of nitrosyl chloride, that is 1.2 squared over partial pressure of NO 5.0 5.0 times 10 to the power 2 squared. Then partial pressure of chlorine, which is 3.0 times 10 to the power -1. Okay, so you do your arithmetic. You square that number on top. You square 5.0 times 10 to the power 2, then you multiply. Okay, so you are going to find your Kp as 1.9 times 10 to the power 3. Okay, so that is the Kp for this reaction. Okay, now look at another example. For the reaction, sulfur dioxide, then plus oxygen. Sulfur dioxide plus oxygen gas then forms the sulfur trioxide. Okay. Write the equilibrium. Constant expression. Write the equilibrium constant expression Kp for this reaction. Then B, what is the value for Kp? What is the value for Kp if Kc is equal to 2.8 times 10 to the power 2. 2.8 times 10 to the power 2 at 1000 K. Okay, so we start. First of all, we write the Kp expression. Okay, so solution. So Kp in this case will equal to the partial pressure. Kp will equal to the partial pressure of sulfur trioxide squared over partial pressure of sulfur dioxide squared, then times partial pressure of oxygen. So this is the expression. Okay, then now B, we need to calculate the value for Kp. We know that Kp is equal to Kc R2 delta N. Okay, so now what we need to do here is to calculate delta N. These others are known already. Okay, so in this case we calculate our delta N. So delta N is equal to 2 minus 3, which is equal to negative 1. That is our delta delta N. Then now we substitute. So it will be Kp is equal to Kc, 2.8 times 10 to the power 2. R we know 0.08206 times T 1000 K, okay, 1000 K to the power negative negative 1, okay. Then now you multiply this number times 1000, so it will be 2.8 times 10 to the power 2. Then it will give you 82 point, it will move 3 decimals, 1 2 3, okay. So 82.06 to the power 1. So then you multiply, you are going to get 3.39. That is our Kp, okay. So that is how we can calculate Kp. Let's now look at heterogeneous equilibria. What we looked at was homogeneous, okay. So we look at heterogeneous equilibria. Heterogeneous equilibria. Okay, heterogeneous equilibria. So this one are reactants and products. Reactants and products are present in more than one phase. Are present in more than one phase. Okay, reactants and products are present in more than one phase. Okay, so concentrations of pure solids, and liquids are fixed, Okay, concentrations of pure solids and liquids are fixed by their density and molar mass and do not vary with the amount. Okay, so in this case we take the concentrations of pure solids and liquids as unity, meaning that they are not supposed to be incorporated in the Kc value. They are not supposed to be incorporated in the Kc value, okay, since their concentration is fixed. For example, write the Kc expression. Write the Kc expression for calcium carbonate solid, then forms the calcium oxide plus carbon dioxide. So you can see this reaction, we have more than one phase solid. We have a solid and a gas. So in this case, Kc will equal to the concentration of carbon dioxide. So we omit concentrations of solids and liquids. In this case, we omit solid. Okay. Another example. B. Copper, 3 copper solid plus 2 NO NO3 aqueous, then plus 8 hydrogen ions, aqueous, then forms 3 copper 2 aqueous, then plus 2 NO aqueous, gas. So this one, it's a gas, nitric, then plus 4 HO2 gas. This one is in liquid form. Okay, so this is the equation. Copper solid, NO3, then hydrogen ion, copper 2, NO plus water. Okay, so casing, remember we omit concentrations of solids and liquids. So in this case, we omit this. So we have copper, so it will be copper 2, concentration of copper 2 cubed, NO squared over NO3 squared, then the concentration of hydrogen ion the power 8. So the concentration of solid, concentration of liquid have been omitted. So we only consider gaseous and aqueous. Okay, so that is how we go about it. All right, so we can end here for this lecture. Then the next one we shall look at predicting the direction of the reaction.